Hello everyone, my name is Sagar Shantilal Tak and I'm here to talk about an ensemble model to predict cardiovascular disease risk that I've built. So let's begin. So these are the contents that I'll cover throughout the presentation here. I'll talk about the data set and the business problem. I'll talk about the exploratory data analysis that I did. I will also talk about the data transformation, the feature engineering and its analysis. I'll also talk about the model selection and why I specifically chose that model and the model's performance, validation, and evaluation. I will also talk about the ensemble model finally, and I will finally talk about the summary and the key lessons that I learned from this project. So, what are we actually trying to predict here? I have used a cardiovascular disease dataset which I have derived from Kaggle, which was compiled by Svetlana Ulyanova, which contains 70,000 anonymized patient records with 12 features, including age, height, weight, systolic, diastolic blood pressure, cholesterol, glucose, smoking, and alcohol use, and physical activity, and the target variable cardio itself. Now, the main problem with cardiovascular disease is the primary cause of death globally, and making an early identification of cardiovascular disease can support clinical decision making earlier. So, this is the core reason why we are trying to predict the target variable cardio. The cardio variable here is indicating presence or absence of CVD by zeros and ones, which is no and yes as a binary classification task. So, let's dig in. So this is our data at a glance. We use 70,000 anonymized patient records, 12 clinical features. The class balance here is 50-50, so there is no specific class imbalance here. And the train test split that I've used is 80-20. So for the exploratory data analysis, I have imputed 10% values in 3 columns, then did the unit and type conversion. Then I treated impossible values. I looked at the numerical and categorical distribution. I also looked at the outliers using box plot, and I had to apply a clinical judgment there, as most of the outliers would catch the cardiovascular disease patient. So I only removed the impossible values from my own judgment. I removed overall 90 rows from it. Now for the correlation analysis, I used the Spearman instead of Pearson method because the blood pressure distribution violates the normality here, and the systolic blood pressure had the strongest relationship with the target, while height had almost none, which told me height would only matter through a derived feature like body mass index. The cholesterol was the most discriminative categorical feature, with well above normal cholesterol patients having a much higher disease rate compared to the normal cholesterol patients. For my data transformation here, since the data had no native missing values, I salted 10% of age, weight, and systolic blood pressure to validate my imputation strategy. So for age, height, and weight, I used KNN. We'll take a look at the KNN imputation here. So let's go to the code. So for my KNN imputation, I have divided it into 2 steps. First is the finding of optimal K, and then KNN imputation to the missing values. So first I'll run the code to find the optimal K here. Here I have tested K values on 200 held out training rows and picked the best K by the lowest RMSE, and then reverse scale after, since caret normalizes internally before computing distances. So that is what we will be looking at. So now that we have ran the code chunk to find the optimal K, we'll be looking at the results very quickly. So we can clearly see here that where K is 13, we get the lowest RMSE value. We can also validate this by looking at this graph here. So now that we have found our optimal K, we'll be performing a KNN imputation here. So I have used reverse scaling as I mentioned before, and I apply the same parameters to the test set, and I confirmed here that there is no data leakage. So let's run this code and find out what we get. After we do the KNN imputation, we'll be looking at the regression imputation, and then we'll be looking at the graphical density plots to see if we imputate all the values correctly or not. So now that we have successfully completed the KNN imputation, we'll be looking at the regression imputation, where I've used three cases where AP high is missing and AP low is available, where AP low is missing and AP high is complete, and where both are missing simultaneously, where we use the demographic values to interpret the values there. So for regression imputation, we'll run the code here. I have used the three cases here and looked at the R square summary for all three. And this is the result that we get. We get zero NAs or missing values remaining in the train and the test set. So now that we have a whole complete data, we can also look at the R values here, where we expect less values for the case 3 because we were using demographics for it. And if we quickly look at the imputation visualizations here, we can clearly see how closely we imputate the values here. Like, let's compare the observed values here and the imputate values here. This is a very close imputation. Now, let's move back to the slides here. So now let's take a look at some further data transformation that I've looked upon. I have derived the log body mass index and the mean arterial pressure as two new clinical features and then dropped height, weight, and raw BMI to eliminate multicollinearity. I applied z-score normalization using training parameters only to prevent leakage. The PCA was purely exploratory, and we confirmed that we did not need dimensionality reductions. And finally, the k-means clustering with k is equal to 5 identified 5 patient risk subgroups, and cluster membership was added as a feature to all the three models. So now we'll take a look at the three models that we built. So first is the logistic regression. It acts as an interpretable linear baseline. It tells me exactly how much each predictor contributes to the disease. The C5.0 boosted decision tree because cholesterol and glucose have ordinal threshold effects that a linear model cannot capture, and boosting means each tree corrects the error of the previous one. And KNN simply because cardiovascular disease is fundamentally a similarity problem. So the patient with similar blood pressure, age, and body mass index tend to share the outcomes. Now we'll take a look at the model's performance. So we'll take a look at how the models are running and how are they performing. For logistic regression, I first ran a full GLM across 24 features, then backward elimination at alpha 0.05 and reduced it to 16 statistically significant predictors where I dropped smoke, gender, and diastolic pressure as not significant. The final model used lasso regularization tuned via a threefold cross validation here. As we can see, the model is running, and these are the results that I got, which we'll discuss next. Now, if we look at the model B here, which is the C5.0, I tuned the boosting trials across 1, 10, 20, and 30. Now that we have got results for our C5.0, as we can see, the AUC is stabilized at around 20, which is great here. And if we look at our model KNN classification, we'll run the model. So for KNN, I used a two-stage strategy where I tuned K on a 10,000 row subsample first to keep it computationally feasible. And then I retrained it on a full 55,000 training row using the best K of 250. So let's move back to the slides. So looking at the model performance here, first of all, I optimized thresholds by maximizing F1 out of fold predictions, and I found that all four fell below 0.5, which is clinically appropriate for disease screening. Let's look at the results here. The logistic regression achieved an AUC of 0.7871 and a recall of 80.1%. The C5.0 had the highest recall for all four models at 83.5%, confirming that boosted trees capture nonlinear risk patterns. And KNN achieved 81.6, which is still good on a recall, and the AUC of 0.7918. The Ensemble achieved the highest overall AUC of 0.7938 with F1 score of 0.74 and a recall of 79.2, which is the best overall balance across all metrics. Now, For validation, the 80-20 split was done before any of the processing, and all imputation parameters, scaling statistics, and the cluster centroids were learned exclusively on the training data with no leakage anywhere. The threefold cross-validation was applied to all three models for hyperparameter tuning, and out-of-fold predictions were saved and used to train the Ensemble meta-learner. So the Ensemble never trained on inflated in-sample predictions, and the final metrics were reported only on the 13,961 held out test observation that no model ever touched during training. So now let's finally dig into the Ensemble model. The Ensemble here works in two stages. In the first stage, each of the three base model is trained with threefold cross-validation, and out-of-fold predictions are saved. And these are the prediction each model made on rows it never trained on. So they are honest estimate. In the second stage, those out-of-fold probabilities from all three models are fed into a logistic regression meta-learner, which learns the optimal way to combine the three specialists into one final prediction. I also built a completely reusable prediction function. I applied it to a hypothetical 55-year-old male, described the statistics on it, and the logistic regression assigned 86% disease probability, the C5.0 assigned 96%, the KNN assigned 87%, and the Ensemble combined all three models into a final probability of 87%, correctly classifying the patient as positive for cardiovascular disease. The strong agreement across all three models gives us high confidence in that prediction, and on the held out test set, the Ensemble achieved the highest AUC of 0.7938, outperforming all three individual models and confirming that combining diverse decision boundaries captures more signal than any single algorithm alone. And so, to wrap up, what we built is a completely end-to-end cardiovascular disease prediction pipeline, from controlled imputation experiment through clinical feature engineering, patient risk clustering, three tune-based models, and a stacked heterogeneous ensemble achieving AUC of 0.7938 on 13,961 held out patient. What we critically found here is that the most important predictors were systolic blood pressure, age, cholesterol, and body mass index, which were consistent with established cardiovascular risk factors and confirmed independently by both the Spearman correlation analysis and the logistic regression backward elimination results. And the key lesson that I learned here is that threshold optimization matters as much as model selection in clinical screening tasks. Lowering the decision threshold from default 0.5 improved the recall by approximately 15% across all models. When the cost of a misdiagnosis is high, how you set the threshold is just as important as which model you pick. So thank you so much for watching. I hope you enjoyed the walkthrough and found the project interesting. If you have any question, feel free to reach out.